In this video, we're going to look again at the Jacobi methods that we introduced in the previous video, but now we're going to ask ourselves the question, when is it stable? When will it not blow up in our faces? So if we look at the formula that we had last time, then we had the following thing. So at iteration n, you calculate basically the error that you have when you insert the field at that point in the equation. So plus fi minus 1 at iteration n, and then we have delta x squared k squared fin. And this thing is proportional to the difference between the new value and the old value. So fn plus 1 minus fn. Okay, so this is the Jacobi method that we've introduced earlier. Ideally, we would like to say something about the convergence of the method. So if you start from a certain given initial guess, can you then guarantee that you always will end up at a true solution? So that's a bit of a tall order. That's a bit difficult to do. So therefore, we're going to look at a slightly simpler but also important problem, and that is the stability. Stability demands basically that if we start from a finite initial guess, and we keep on running the Jacobi machinery, that we will never have the situation where we get infinite values, that the whole thing diverges and blows up. So it's a necessary condition in order to get convergence, but not a sufficient one, unfortunately. But still, very important. So how are we going to tackle this? Well, rather than looking at the fields at a certain iteration directly, we're going to write the fields as a sum of Fourier components, as a sum of plane waves, basically. So exponential minus j kx. And then we're going to check the stability of each possible plane wave. So if we can guarantee that this whole thing is stable for all possible plane waves that you have in your system, then basically, because of Fourier analysis, you can guarantee that the whole thing is stable for all possible fields that you will enter into your iterative scheme. So that's the task. So basically, we're going to assume that we start from a certain iteration fin, where we have a discretized plane wave, exponential minus j kx I x, basically, I delta x. But this is our plane wave that we have at a certain moment in our iteration scheme. And then the question is, what happens if we calculate the next value of the iteration? And more importantly, what happens if you take the ratio between that new value and that old value, that you basically want that this thing stays smaller than 1, otherwise it blows up. So that's the whole thing that we're trying to guarantee here. Okay, so pause the video. Take this particular initial field distribution, plug it into the Jacobi equation and see if you can calculate that ratio, and then we can try and figure out when exactly it stays bounded. Okay, just some straightforward algebra here. So for the first term, if we plug this thing in here, so then we have f at I plus 1. So it's going to be exponential minus j kx I plus 1 delta x. Then we have minus 2 times exponential minus j kx I delta x. And then we have exponential minus j kx and then I minus 1 delta x. So these are these terms taken care of, coming from the second order derivative. And then we have this guy over here, which is going to be delta x squared, k squared, and then fin, which is exponential. Let me have some more space here. Exponential minus j kx I delta x. Okay. And that should be equal to alpha times the difference between the new field and the old field. So the new field that we're going to calculate is this guy, and the old field is exponential minus j kx I delta x. Okay, so that's basically what we have here. So now let's try and isolate fi n plus 1 here. So what we're going to do is first focus on the right hand side and then expand this. So we have, let me again start a bit lower because these exponentials take up a lot of space. So alpha fi n plus 1 minus alpha exponential minus j kxi delta x is equal to, and then we have that that big left hand side here. Now everywhere you see that we can factor out an exponential, so let's do that. So this is going to be exponential minus j kxi delta x, and then times, and then let's collect all of the other things that we have. So starting over here, we have exponential minus j kx delta x. And then we have, for the next one, we have minus 2. And then we have exponential plus j kx delta x. The two minus signs will cancel. And then finally, we have that constant term here, which is delta x squared k squared. Okay. Almost there. Yeah, let's bring this thing to the right hand side where we can again factor out this common plane wave here. So finally we have that exponential, sorry, that alpha times fi n plus 1 is the exponential that we factor out, kxi delta x times. So then we, if we bring this thing to over there, then we have an extra alpha. Now let's take a look at these two exponentials over here. At this point in time, you hear Euler whispering in your ear that you can combine those into a cosine. So this becomes 2 times the cosine kx delta x minus 2, and then we have delta x squared k squared. Right. Now comes the fun part, and that is that you realize that this prefactor here is actually the original field that you started from, fin. And by the way, that's precisely the reason why we're trying to solve this problem in the Fourier space with plane waves, because plane waves turn out to be eigenfunctions of the Helmholtz equation. So this is why they keep on popping up here, and then you can factor them out as an eigenfunction, and therefore you can bring them again to the left-hand side to finally come up with the ratio between the old and the new fields, fin plus 1 divided by fin. That ratio is actually, so if we divide everything here in between square brackets by alpha, then we have 1 plus, and then we have 1 over alpha, and then another set of square brackets. That's then 2 times cosine kx delta x minus 2 plus delta x squared k squared. And this is the ratio that we have between the old field and the new field. And in essence, what we want is that the absolute value of this ratio, that this thing does not blow up. In the worst case, it can stay the same, probably not converge, but in any case, we want to avoid that this thing becomes bigger than 1, so that it becomes unstable. Right, and this thing should hold for all possible values of alpha that you pick. And remember, alpha is a positive number, and it should also hold for all plane waves that you study, and for all other values that you pick here related to the inverse wavelength or the discretization step. So pause the video and think about when you can guarantee that this thing does not blow up, or at least come up with a necessary condition for this thing to be stable. So let's have a look at this. So what we would like to have is that, let's look at the upper bound here. So this thing, this whole thing, should at least be smaller than 1. This is a positive number. Here we have our 1. So this can be smaller than 1 only if this thing between square brackets here is actually negative. If this thing is negative, then we end up with a number smaller than 1 here. So that's a necessary condition. It's not sufficient because we also need to guarantee that this thing does not become too negative so that it overshoots and becomes smaller than -1. But let's focus on the necessary condition to derive our stability criterion, because necessary conditions are, of course, necessary. So we need that the stuff between square brackets is negative. Okay. Worst case can be equal to 0. If this thing should be negative, then we should have that 2 times cosine kx delta x minus 2 should be smaller than minus delta x squared k squared. Okay, that at least will guarantee that for alpha no longer plays a role here. So now we have this condition to look at. Let's look at the bounds of the left-hand side. Now we know cosines can take values from -1 to 1. And that means that if we look at the range of the left-hand side here, if we have -1, then we have -2 times -2. So we go from -4 to, and if we have 1 there, then we have 2 minus 2, 0. So this thing here is from -4 to 0. Now, this 0 value is a quite important one because that happens when you have kx equal to 0. So if kx is equal to 0, then you have the cosine of 0 is 1. So then you have this upper bound here. So this is a really important situation because this is in essence the DC component of your field. And your field will obviously in almost all situations have a DC component. So we really need to make sure that when you're looking at the DC component that you have stability there. But here you see that that's not guaranteed here, because if you're looking at the DC component, then you have 0. But this thing over here, yeah, is a negative number, right? So 0 is not smaller than a negative number, and therefore that means that you will not have convergence and your DC component will keep on getting amplified in the Jacobi scheme and will eventually blow up. So that's a bummer. The Jacobi method does not really work for the Helmholtz equation. It does work when you put k equal to 0, but then you're not solving the Helmholtz equation, but you're solving the Laplace equation. But for the Laplace equation, indeed, the system is stable, and then you might think of using this particular Jacobi method. So it's unfortunate that this thing does not work. However, people have been trying some techniques to get it to work anyhow by playing all sorts of clever tricks, by combining 2 iteration steps and then having alpha be a complex number. So there are ways around this, but the general vanilla Jacobi method, unfortunately, only works for the Laplace equation and not for the Helmholtz equation.